Good morning, student. Welcome to the session on sigma and pi explained by molecular orbital theory. So before proceeding to the topic sigma and the pi bond, let's revise the previous session. In the previous session, we have seen the probability distribution curve for bonding molecular orbital and antibonding orbital by taking example of H2 plus ion molecule. So this is the bonding molecular orbital equation. Psi plus square equals to 1 divided by 2 plus 2s in bracket psi a square plus psi b square plus twice psi a psi b. Now we can see here the equation where psi a square plus psi b square plus 2 psi a psi b means this much quantity is added. So in the bonding we will see more electron density between the nuclei of hydrogen atom A and hydrogen atom B. The probability curve can be shown with the graphical representation like this. So these are two atoms that we have taken in an example, hydrogen A, hydrogen B. These are their individual psi square function. Psi square function is used to find the probability of electron in a space. So the first pink dotted curve, this one, shows the probability of finding the electron of HA atomic orbital, whereas this pink dotted line shows the probability of finding the electron in atom B, hydrogen atom B. Now when they combine with the overlap, they will form, these are the probabilities, they will form this blue line, that is psi plus square. So this is the combined wave function. This is molecular orbital wave function, and it gives the probability of finding the electron in the molecular orbital. We can see here the value, that is twice psi a psi b. It increases the probability of electron between the nuclei, and it stabilizes the molecular orbital, and it leads to decrease in the energy of molecular orbital. So this equation with this graph gives us information about first. So before it is the pictorial representation. This is hydrogen atom A and this is hydrogen atom B atomic orbital. They come together, they undergoes proper overlap, and they form molecular orbital, that is bonding molecular orbital. This gives important information for probability of finding electron in molecular orbital. More value than the psi square of individual atomic orbital by a factor of 2 psi a psi b. Then electron behave, or they are in between the center of nuclei, means they are, since they are overlapping very properly, they will place themselves between the nuclei to have a proper bonding. Now since the proper overlap and bonding takes place, it provides stability to the molecular orbital. Since it provides the stability, the energy of molecular orbital decreases, and we can see that bonding molecular orbital always placed below due to the lesser energy. Similarly, for antibonding molecular orbital, for the antibonding molecular orbital, we can see here the value decreases by a factor of twice psi a psi b. The graphical representation, like we have done in the previous slide, for atom A and for atom B, this is the psi square function for both the atomic orbital, like this one, psi square A for A hydrogen atom, psi square B for B hydrogen atom. But when they combine and forms antibonding molecular orbital, the combined wave function can be given as the blue line shown. It is represented by psi minus square, and the value of the electron probability finding between the nuclei decreases with a factor of minus twice psi a psi b. So this is the value. Apart from this, when we see the pictorial representation, we will see here when atomic orbital bond or they overlap and form antibonding orbital, they shows some nodal region. Like this is the pictorial representation. One atomic orbital overlap with the another, they mix to form this antibonding molecular orbital. Now this node is nothing but the probability of finding the electron in this space is 0, or it decreases to 0 due to the antibonding molecular orbital formation. Apart from this, it gives three important information. The first, less probability of finding electron in molecular orbital by a factor of -2 psi a psi b. Then the probability of finding electron between the nuclei is very less. They remains closer to the nuclei. They do not want to form overlapping. That's why they remains nearer to the nuclei. That's why they do not contribute in the stability and the increase and their result in the increasing energy of molecular orbital. So its increase, or it is having more energy compared to bonding molecular orbital, and it is placed above. Now next important thing is, up till this we have seen the wave function for linear combination of atomic orbital, wave function for individual atomic orbital, then combination formation of molecular orbital and formation of bonding and the anti-bonding molecular orbital. The important aspect we learn from this is how they overlap, how they relate with the probability of finding the electron between the nuclei, or they are nearer to the nuclei, or the energy and the stability. Now in this aspect, when we deal with the thing that how atomic orbital overlap in a space, how atomic orbital interact with each other to form different molecular orbital. This gives information about the energy as well as its stability, and somewhere or other it leads to some practical application, that is spectroscopic analysis of symmetry, how the symmetry help in analyzing the molecular orbital. So let's see the sigma and the pi molecular orbital. This is our topic. Now let's collect all these small things. One atomic orbital, another atomic orbital, when they combine, they use molecular orbital. Now this overlap is important. As far as molecular orbital is molecular MOT is concerned, that is molecular orbital theory, this overlap plays an important role, because if they overlap in a proper way, in a comparable way, they leads to the molecular orbital. But if they do not overlap, there is no formation of molecular orbital. So overlap is must. When two atomic orbital or more than two, but for example we are taking the example of two molecular orbital, combine, they overlap to give molecular orbital. This molecular orbital will have two different energy that we already determined by using quantum mechanical formulation as well as the quantum mechanical operator. One energy will be less and one energy will be high. Okay. Now this low energy and high energy are coined with some term. Low energy molecular orbital are said to be bonding molecular orbital, whereas high energy molecular orbital are said to be antibonding molecular orbital. Now this is very basic. Whether the atomic orbital overlap to form sigma or atomic orbital overlap to form pi molecular orbital, they will definitely show different energy level. The energy level which is having low energy will be bonding molecular orbital. The high energy level will be anti-bonding molecular orbital. So this is common for all molecular orbitals. Now let's see how overlap can have different cases. Basically overlap can be categorized can be in two ways. The first will be axial overlap. The axial overlap means when atomic orbital approaches each other, they interact with their own axes. Okay, means if we take the example of atomic orbital 1, if it is moving with x axis, and other is moving also with the x axis, then if they overlap, it will be the axial overlap. And sometimes in a simple language it is also called as head-on overlap. Then next case of overlap is the lateral overlap. This lateral overlap basically when the orbital is moving but the orientation is perpendicular to the moving axis. Since they are approaching in a sideway manner, this is also commonly called as sideway overlap. Axial overlap result in sigma molecular orbital and lateral overlap result in pi molecular orbital. Now, this axial leads to sigma, lateral leads to molecular orbital. Means how atomic orbital mixes to give the molecular orbital. When they have maximum interaction in an axial overlap, it leads to sigma molecular orbital. But when they overlap laterally, it leads to pi molecular orbital. Now, this sigma molecular orbital, when formed, it will have two energy. One is lower and one is higher energy. The lower energy is called as the sigma bonding molecular orbital, whereas for the antibonding, it is called as sigma star antibonding molecular orbital. This star represents the antibonding nature of molecular orbital. Similarly, when pi molecular orbital form, it also gives two different MOs, that is molecular orbital, one with lower energy and one with higher energy. Lower pi molecular orbital is represented by pi, whereas higher energy molecular orbital is represented by pi star. Now, this is how the overlap leads to different molecular orbital. When overlap of atomic orbital takes place axially, they form sigma molecular orbital and they will have two different energy level. Low energy level is said to be sigma bonding and the high energy level is termed to be the antibonding. When the atomic orbital overlap laterally, they form pi molecular orbital. They will have two energy level, two MOs, that is molecular orbital. Low energy MO will said to be pi bonding molecular orbital. High energy molecular orbital will be said to be pi antibonding molecular orbital. Now this is how the overlap result into different molecular orbital. Now let's see how pictorial representation can be done for this. This is simple XYZ Cartesian coordinate, a space coordinate. This is p orbital. This p orbital is aligned with the x-axis. This is one atomic orbital. This is another atomic orbital. This is also aligned with the x-axis. When x aligned orbitals, two atomic orbital interact and overlap, this is called to be the axial overlap and they will form sigma molecular orbital like this one. This is head-on sigma molecular orbital. This can be shown by two arrows interacting axially like this. When they move, they undergoes overlap. So this is head-on collision which result in head-on overlap which result in sigma molecular orbital. Now let's take how pi bond molecular orbitals are formed. So this is again p orbital with orientation perpendicular to the x-axis. This is one. This is another p orbital. Again the orientation perpendicular to the x-axis. When they interact, they will have sideway overlap result in pi molecular orbital. How they will overlap? The pictorial representation will be, this is the upward arrow, this is another upward arrow for other atomic orbital. When they interact, they will form molecular orbital. So this is the simple pictorial representation how molecular orbital are formed. If the atomic orbital interact with axial overlap, they form sigma molecular orbital. But when atomic orbital interact sideway, they form pi molecular orbital. Now let's see the case of this. Now this is again x-axis. We can see here both atomic orbital are aligned with the x-axis. Obviously when they overlap, they will be head-on overlap and form sigma molecular orbital. When sigma molecular orbital form, the energy level will be distributed. One will be having higher energy and one will be having lower energy. Higher energy level molecular orbital will be called as bonding. Higher molecular orbital will be called as anti-bonding, whereas lower molecular orbital will be called as anti anti-bonding. So basically, let's revise again. The lower molecular orbital will be termed as bonding, and the higher molecular orbital will be termed as anti-bonding. So let's see. This is how they interact. First case. This is the first lobe. This is the second lobe. These two dumbbell-shaped p orbital. If we see here, the positive as well as this positive are there on the axis, they are head on. This positive when they interact, they have maximum probability of electron between the nuclei. They will have more overlap. Now student may confuse here, the positive charges repel, like charges repel, but do not misunderstand this positive charge with the charge. Basically these are the sign for maximum probability of electron, means the finding the electron in this space is more for this p lobe, whereas finding the electron in this space is more for this another atomic orbital. So when they interact, they form sigma p orbital, because due to the highest probability of electron between the two nuclei, electron density here will be more. They will stabilize the molecular orbital and the energy decreases. Since energy decreases, it forms sigma molecular orbital. So this is the first case. Let's take second case. So the first lobe remains same without any change in the alignment, but let's reverse the second atomic orbital. Now if we see here, in the first lobe the positive sign and in the second there is a negative sign. So when they overlap, the electron density decreases, which leads to instability and increase in the molecular orbital. Since the molecular orbital is having higher energy, this is termed as anti-bonding sigma molecular orbital. Okay, this is how the bonding as well as anti-bonding molecular orbital form for this sigma molecular orbital. When the positive charge are in the axial overlap, they will form sigma molecular bonding molecular orbital. But when the opposite sign orbital interact, they will have higher energy and they will form sigma anti-bonding molecular orbital. Now this is how the sigma bond forms. Now see, this is again simple nomenclature. The upper one is said to be the sigma p bonding molecular orbital. The bottom one is sigma p anti-bonding molecular orbital. Now let's see the lateral overlap interactions. So when the lateral overlap takes place between these two atomic orbital, they will also form molecular orbital, and this molecular orbital is said to be due to the sideway overlap, which result in pi molecular orbital. Pictorial representation will be two upward arrow interacts with each other to use the molecular orbital. Now if the molecular orbital form, it will have two energy. One energy will be less, which will be said to be the bonding molecular orbital, and another energy will be high, said to be anti-bonding molecular orbital. Now let's see how this pi molecular orbitals form. So if we see here, these upward oriented p orbitals are aligned in the same direction, or the positive and the negative have the same phase. When this type of orientation overlap, they have maximum electron density to form bonding molecular orbital. So This is called as the pi bonding molecular orbital. This p, because these are nothing but the p orbitals, atomic orbitals. Now take the next example. The first lobe is same, but the second lobe reverse its orientation. Now we can see here this positive and the negative ions, if they interact, the overlap will be less, because here the electron density is more and here the electron density is less. Obviously the overlap will be minimum and the energy level increases due to the lower overlap. Since energy of this molecular orbital is more, this is termed as anti-bonding molecular orbital, and it is represented by pi star p. This is how two molecular orbitals form by the pi molecular orbital formation. The lower energy molecular orbital is said to be bonding molecular orbital. The higher energy molecular orbital is said to be anti-bonding molecular orbital. This is how that we explain pi. The upper one will be the pi p bonding molecular orbital. Bottom one will be, this is pi anti-bonding molecular orbital. Now the difference between sigma and the pi molecular orbital. This is the concluding how we can compare it. It will be related to how it forms and how related to some electron density. The first difference will be the sigma forms with the axial overlap, whereas the pi formed by the lateral overlap. Second, there is a symmetry of electron in the internuclear axis, means they will have more symmetry of electron between the nuclei, they combine, whereas there is no symmetry in case of pi when the electron density is between the nuclei. This point I will discuss in the later slides. We have our next slide for the symmetry and the unsymmetry. Since overlap in case of sigma molecular orbital is more, it forms a larger overlapping, leads to lower energy, whereas in case of the pi molecular orbital, the overlap is small. That's why the lowering of energy is not so good. Nodal plane is observed, no nodal plane is observed in case of sigma, whereas nodal plane is observed in case of the pi. Now the Gerade and ungerade parity of molecular orbital. Now this is the important property of molecular orbital, which is important to learn with respect to its spectroscopic analysis, its spectroscopic application. Basically, the molecular orbital, when they have symmetry, okay, and when they have unsymmetry, they have some transition rule, that is a selection rule for the spectroscopy, and this is the application. If we know the symmetry of the molecular orbital, we can easily relate it with its transition in the electronic spectroscopy. Now, what is the meaning of Gerade and ungerade? Basically, this Gerade is a Greek word which means even or the symmetry, whereas ungerade in Greek means uneven and symmetry. अगर हम लोग हिंदी की बात करते हैं तो even का मतलब होता है समानता, मराठी में समान, और जब हम लोग अनइवन की बात करते हैं तो हिंदी में उसका मतलब होता है असमानता और मराठी में असमान. So whenever we see any structure, we can categorize it either symmetry or asymmetry. Okay, but on which basis we can classify the any material or anything symmetry or asymmetry? So let's take one example. So this is beautiful sunflower. If we see here, we can see it is very symmetrical. Why it is very symmetrical? Because if I draw a line from its center to the periphery, the distance will be same, like this. That's why this flower is very symmetrical. Similarly, if we take the example of lemon, okay, this is half cut lemon. This is again a very symmetrical structure, because if I draw a line from center to its periphery, the distance will be same. That's why it is symmetrical. Now, if we consider these two examples and let's relate with this one. This is our palm. Is it symmetrical? No, it is not symmetrical because we cannot have equal distance from the center of palm to the periphery. That's why this is unsymmetrical. So for the first structure, it is Gerade symmetrical. For the second structure, this is again symmetry, and in the third, this is Ungerade asymmetry. Now let's see how we can use this symmetry element for molecular orbital. For the molecular orbital, this is understand with a simple term, that is centrocentric molecular orbital. So what are centrocentric molecular orbitals? The molecular orbital with center of symmetry. This we have to understand. Center of symmetry. What is the center? This is the inversion center, the point from which there is equal distance to the periphery, and there will be same sign on the both side. So let's take example. This is s atomic orbital, another s atomic orbital. If they combine, they form molecular orbital with this shape. Okay, now if we see here, the positive positive same atomic orbital, if they overlap, they will form sigma s molecular bonding orbital. Okay, because the same charge same charge atomic orbital overlap. Now if we take the distance of this center to the periphery and distance of this center to the periphery, these two are same, means this is symmetrical in nature, and it started from this positive this to this positive. That's why it is represented by sigma g, because g represents the G rate, and this is sigma G rate molecular orbital. From which factor we have determined it? From the inversion center. Center of symmetry is nothing but the inversion center. Means if I draw a line from this point to this and a line from this point to this, the distance will be same. So this is the center of inversion, and they have the same charges. Let's take the another formation. This is one s orbital, this is another s orbital with negative. If they overlap, they will form molecular orbital, anti-bonding molecular orbital, which represent like this. Now this point, this pointed points are nothing but the nodes, okay, where the finding or probability of finding the electron is less. So since two opposite sign overlap takes place, this is anti-bonding molecular orbital represented by sigma star s. Now let's see what is the symmetry. This is not a symmetrical structure, because if I draw a line between these two and take the distance, it will have positive charge and negative charge. So the center of inversion is lost here, and it is considered as sigma star u, that is ungerade. Okay. So two things are required to consider the molecular orbital as a symmetrical. First, it should have center of inversion, and second, when the arrow started from a sign, it should end to the same sign. Means if arrow started from the positive sign, it should end at the positive sign. Then and then we can call that molecular orbital Gerade or symmetrical. If arrow started from one sign and in at the other sign, it is considered as uneven and represented by the ungerade, means u. Let's take, this is the G even parity and u uneven parity. Now let's take the p orbital sigma bond formation. This is p orbital sigma bond formation again. Same axis, they will interact to give molecular orbital, this one. So this is the sigma p orbital. Now if we want to consider the symmetry part, okay, does it have symmetry part? The answer is yes, because if I take this as an inversion center and take this one, means the arrow started from the negative and ends at the negative means it is symmetrical in nature, will have equal part, and it will be represented by sigma g. Okay, so this is the sigma bond formation between p orbital. Let's take another. Okay, now we can see here when they interact, okay, they will form this antibonding molecular orbital. This antibonding molecular orbital means it is represented by sigma star p. Now let's see its symmetry. Is it symmetrical? No, it is not symmetrical, because when the arrow started from positive, it ends at the negative, means it is unsymmetrical. So it is represented by sigma star u. Now let's see for the pi orbital. This is the first case when the orientation is at the same side and they interact with the positive sign. Okay, so basically they will interact to give maximum overlap to have the bonding molecular orbital. It will be observed like this. This is bonding molecular orbital, it is pi p. So whether it is symmetrical or not. So basically it is not symmetrical, because if we cut it and we start from positive, it will end at the negative, means it is unsymmetrical. It is pi u. Now let's see for the anti-bonding molecular orbital. We can see here this is the first atomic orbital and having the orientation reverse, the positive negative will interact to form molecular orbital, that is anti-bonding molecular orbital. Now let's see its symmetry. Basically it is anti-bonding molecular orbital represented by pi star p. Then let's take its symmetry element. We can cut it like this, and it started from negative and ends at the negative, means it will be symmetrical. Basically there should be G. Now let's revise all the molecular orbital with its geometry. So this is sigma s atomic orbital. If it started from positive end to negative and ends at negative end, this is sigma G. Then next one, this is anti-bonding sigma molecular orbital. If we take the arrow from positive, it ends at the negative, means it is unsymmetrical, that is sigma star u. Now this is bonding p orbital. The symmetry negative, from arrow started from negative ends at the negative, it is represented at sigma g. Then anti-bonding p orbital, sigma p orbital, it started from positive and ends at the negative, means it is uneven or u, sigma star u, p orbital. Now pi bonding. For pi bonding there is no symmetry, it is represented by pi u. And at last pi anti-bonding, there is a symmetry, because it started from positive and ends at the positive, so this is pi star g. So here we conclude the lecture. We have learned the symmetry element of molecular orbital and its formation, how the sigma and how the pi orbital form. When the lower energy is called as the bonding and the higher energy is called as the anti-bonding. When the symmetry element are observed for the molecular orbital, we can categorize these into two categories. Gerade means symmetrical, ungerade means unsymmetrical. Gerade is represented by G, whereas unsymmetrical is represented by ungerade U. Okay, so if we see the sigma bond formation, in the sigma bond formation, bonding orbitals are symmetrical, whereas anti-bonding are unsymmetrical. But for the pi, the bonding orbital is unsymmetrical, whereas for the anti-bonding it is unsymmetrical. So here I conclude, if somebody is having any doubt or any question, they can give their question, suggestion or any doubt in the link itself. I will definitely try to solve those questions in our next session. Thank you so much for your patient listening.